Alright, here we have lecture 2.4, which will correspond with section 3.3 from the textbook. Alright, and here we introduce and describe behavior of functions, and we can learn a lot about the behavior of a function by studying its graph. For example, we can figure out where a function is increasing and where it is decreasing, and this is very crucial in a variety of applications and will be huge in Calculus 1. So function f is increasing over interval I if for every pair of x values in interval I such that you're reading from left to right, the left point is lower than the right point. It's essentially what that definition is saying. This inequality is just making sure we read from left to right, and this inequality is just saying the left is lower than the right point. And this quantifier for every is very important. So we know this graph is increasing because it doesn't matter what 2 points I pick. If I pick these 2 points here and here, then the point to the left is always going to be lower than the point to the right. That means it's increasing. And we know it's decreasing if the point to the left, so suppose I pick this point, then its y value is right around here. And I pick this as my second point, its y value is right around here. We can see that the left point is higher than the right point and thus decreasing. So that is increasing versus decreasing. And a quick little tip, we are going to be using x intervals to describe where a function is increasing or decreasing. Alright, so that brings us from, and we'll do more examples later, but I want to introduce extrema next. Now, extrema is just going to be another word for minimums and maximums. Now, we have two different types of extrema, what's known as local extrema and absolute extrema. So we'll start with our local extrema, and your local extrema can come in the form of local maximums or local minimums. A local maximum is at some point if there exists a neighborhood around it such that it is the highest point. So as you can see here, we have a local max right there. That's because I can create a neighborhood around that such that every other point in that neighborhood is going to be lower than that local maximum. Now this point right here is not a local maximum. That's because it doesn't matter how small I make the neighborhood. I can make a teeny tiny neighborhood around it. Doesn't matter how small you make the neighborhood around that point, you will never be able to create a neighborhood around that point such that every point in the neighborhood is below it. Points to its left will always be a little bit higher because it is decreasing in that sector. So, little tip here. Local maximums look like peaks. So anywhere you have a peak in your graph, you're going to have a local maximum there. And then the local minimum is very similar. Here we have a local minimum because there exists a neighborhood. So we can create a neighborhood around it such that it is the lowest point in the neighborhood. So your local minimums are going to be like your valleys. So local min look like valleys. And a nice little thing to be aware of, whenever a function switches from increasing to decreasing or vice versa, I should say a continuous function, but I digress, switches from increasing to decreasing, or vice versa, then there will be a local extrema there. Now, if it switches from increasing to decreasing, you'll have a local maximum. If it switches from decreasing to increasing, then you'll have a local minimum. And then your absolute extrema, those are points that are the absolute highest or absolute lowest. So not all local extrema are absolute extrema, but some of them are. So let's go ahead and practice with some examples. So here it asks us to provide info. So what we want to go ahead and do here is determine if it's a function, and the answer is yes, it passes the vertical line test. What's the domain? Well, if you look at the arrows, it goes left forever and right forever, so it's negative infinity to positive infinity. So range is the y values. The lowest it goes is -1. The highest it goes is positive infinity. X-intercepts, it touches the x-axis at -1, 2, 4. Y-intercepts, crosses the y-axis at 2. G at 3, so that's right here. We have 3, -1. So when we're at x value 3, the graph is down at -1. And here we get to the new stuff. So when we're describing increasing and decreasing, where a function is increasing and decreasing, we'll describe it in terms of an x interval. So it's always an x interval. So it's increasing from here to here. So from here to here, it's increasing, and it's also increasing from here forward. So there's two sectors where this graph is increasing. It's increasing from -1 to 0, union 3 to infinity. Now notice I'm not using brackets there. I'm not using brackets because it's not increasing at those exact points, because at those exact points it's switching from increasing to decreasing. So it's neither increasing nor decreasing at those points. You'll learn more about that in calculus. The derivative there is 0. But also, we are using x intervals here. So we don't care about the y values when we're describing where a function is increasing or decreasing. We're just looking over what x values is it increasing, over what x values is it decreasing. So if we want to look for where it's decreasing, well, it starts decreasing from the beginning, and it keeps decreasing. It's going decreasing, 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 decreasing. Does it stop decreasing here? Nope. Decreasing, decreasing, decreasing until we get to here at this x value at -1. And then it starts decreasing again right here at x value 0. So remember, we're looking at x intervals, not y intervals. So this is at x value 0, decreasing, decreasing, decreasing. It doesn't stop decreasing here. It keeps decreasing until we hit this local minimum. So it's decreasing from 0 to 3. And there you have it. And then once we hit x value 3, it starts increasing again. And it just keeps increasing from there. So local minimums, those are kind of like our valleys. So if you look, we have two of them. We have a local minimum at -1, 0. And also at 3, -1. And then for our local maximum, those are like our peaks. We only have one peak at 0, 2. And are there any absolute extrema? Yes, there's an absolute minimum, and that's at 3, -1. So that's the lowest the graph goes. And then for what x values does g at x equal 2? So what inputs give us an output at 2? Well, if we input, let's see here, -2, we get 2. At 0, we get 2. And at 4.3, we get 2. All right. Let's go ahead and look at another example. So this is a function. Its domain is all real numbers. Its range is also all real numbers. It goes down forever and up forever. X-intercepts, there's only 1 at 2. Y-intercepts, there's only 1 at 3. F at -2 is at +1. And where is it increasing? So it's increasing from -2 until 0. So that's the only place in the graph where it's moving upwards. Everywhere else it's decreasing. So it's decreasing from negative infinity until negative 2 union 0 to infinity. And local minimums, those are like your valleys. So it's got a low point at negative 2 comma 1, and it's got a peak at 0 comma 3. Alright, and are there any absolute extrema? Nope. If it goes down forever and up forever, you can't have a highest or lowest point. If it goes up forever, there's no highest point. If it goes down forever, there's no lowest point. So, last topic here, and sorry I forgot to prep this before I started recording, so you'll have to bear with me as I write, is even and odd functions. And this has to do with symmetry. So we covered symmetry in the very first lecture from Unit 2. So a function f is even if f at negative x equals f at x. In other words, a negative input doesn't matter. Now there's a theorem that's very important here, and it states that a function is even if and only if it is symmetric to the y-axis. And then we got odd functions. A function f is odd if f at negative x equals negative f at x. So a negative input is going to give you the negative of the output. In other words, now that one's a little more confusing. The best way I can use to describe an odd function is that it means the same thing as symmetric to origin. So function is odd if and only if, there's that biconditional again, if the function is symmetric to the origin. So in other words, in summary here, a little tip, a function is even if and only if it's symmetric to the y-axis, and it's odd if and only if it's symmetric to the origin. And a quick warning here. It is possible for a function to be neither. Right. Because you can have a function with no symmetry at all. So it is possible for a function to be neither odd nor even. So just because a function's not even, that doesn't automatically mean it's odd. It could be neither. And we've already covered this, so there's no point in doing any examples. Even just means symmetric to y-axis. We talked about that in the very first lecture in Unit 2. Odd means symmetric to origin. We talked about that in the very first function. The only tip I can write here is keep in mind f at x slash function notation is interchangeable with y. So what that means is determining if a function is even or odd is no different than determining its symmetry. Alright, cool beans. So that is behavior of functions down, and have a wonderful day.